Welcome. Today we'll be going over an interesting effect in free radical polymerization that really links our theory to our experiments. As is already known, free radical polymerization is defined by three major steps. We have initiation, propagation, and termination. In these chemical reactions, I'm showing you the polymerization of styrene, but most importantly, what I want you to take away from this is that during initiation, we have a rate constant of initiation, propagation, a rate constant of propagation, and same as well for termination, where there is a rate constant associated with combination, disproportionation, which we can combine as a rate constant of termination. Let's say we have a sample vat of initiator and monomer, and we activate our initiator, thereby forming our polymer chains. And these polymer chains, with now active centers, will interact with monomers spread all throughout the solution to propagate, and therefore this will go under the rate constant of propagation. Eventually, these polymer chains will interact with one another as monomer becomes more sparse and will terminate to form our final solution. Therefore, what we can see is we'll have an overall rate of polymerization, which will be defined with our rate constant of propagation, initiation, and termination, as well as our fractional conversion and our concentration of monomer and initiator. However, what experimentalists have found is that in those solutions, what would happen is they would quickly become very viscous, which is definitely not useful to be processed in large-scale manufacturing. Let's say you had a large vat with a turbine inside. The quick gelification would prevent the solution from being stirred further. As well, what they have found is these solutions could often cause a lot of smoke and would become very, very hot, which obviously very dangerous and very unsafe. What is it due to? This is due to the auto-acceleration effect, also known as the gel effect or the Tromsdorf-Norrisch effect. If we take again our sample vat of monomer and initiator and activate it, we will again form our polymer chains. And these polymer chains, however, will take up most of the available volume in the solution. Due to steric repulsions and electrostatic interactions, these polymer chains will basically become fixed in place thermodynamically and kinetically. However, our smaller monomers will be able to move around freely and still interact with our growing polymer chains. Therefore, our rate constant of propagation will still remain unchanged. However, these polymer chains, not being able to move around as much, will have a less likelihood of terminating with one another. Therefore, our rate constant of termination will be theoretically decreased. Now, what would happen if we were to plug this into our equation? Well, what we'd find is that as our Kt decreases, our rate of polymerization will drastically increase. So what does this mean? Well, eventually what will happen is we'll form very long chains very rapidly, and as we know, with a longer or higher molecular weight of our polymer chains, the viscosity will drastically increase for a solution. What we find as well, again, is here this is the conversion of MMA at 50C in benzene, where each line showcases different initial monomer concentrations, and with higher monomer concentrations, the conversion rate will definitely be higher, as we can see with 100% here and 10% over here. What does this mean? Well, with a high conversion rate, what will happen is, as we know, our free radical polymerization being exothermic will increase the temperature in the solution very rapidly. This rapid conversion with rapid temperature increase could cause the solvent to vaporize, and therefore creating a nauseous vapor, and subsequently also increasing the viscosity, and eventually forming a gel. Overall, being a very uncontrollable reaction and very unsafe. How can we decrease this autoacceleration so that it could become more processable for large-scale manufacturing? Well, what we can do is we can decrease our initial monomer concentration. By doing so, we'll have a more dilute solution in which the polymer chains will be more freely able to move around and will have a higher likelihood of terminating with one another, and therefore going back to our initial theoretical system as we had seen previously. As well, what has been done is experimentalists have determined with a high shear rate, you could allow for polymer chains to move more freely, and therefore, again, go back to our theoretical system, which would definitely be easier to process, and overall making a safer system. Thank you very much.